Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearsonate Excel International A-Level Chemistry Unit 2 for January 2024. Let's begin with the first question. In question 1, which compound has intermolecular hydrogen bonding? Intermolecular hydrogen bonding exists between hydrogen fluoride molecules, so the answer should be A. According to your textbook, intermolecular hydrogen bonding exists between water molecules, between hydrogen fluoride molecules, and between ammonia molecules, although there are other molecules that have intermolecular hydrogen bonding, but those have weaker forces, so the most outstanding ones are between the three I've stated. In question 2, in which process are intermolecular hydrogen bonds broken? So here, between hydrogen molecules, we do not have intermolecular hydrogen bonds, so that's out. Between hydrogen here as well as there we do not have, but intermolecular hydrogen bonds exist between water molecules, so converting water liquid to water gas involves breaking intermolecular hydrogen bonds, so the answer should be B. A compound contains molecules with non-polar bonds, meaning there is no difference in electronegativity between the two atoms involved in the bond. It also has permanent dipole forces between its molecules. They say which could be the formula of this compound. Use the data booklet as a source of this information. The nitrogen-oxygen bond is polar, so that is out. Beryllium chloride is going to be polar. Tetrachloromethane is going to be polar. However, the molecule is non-polar because there is symmetry. So the answer is going to be C, pH3. In question 4, which alkane has the strongest London forces in the liquid phase? So if we are comparing just alkanes, we have to look at the number of carbons. This has 5 carbons, that has 5 carbons. Here we have 9 carbons and here 9 carbons. So those with 5 carbons can be cancelled out. But the one with 9 carbons that is not so branched is going to be the one with the highest boiling point. So D is the answer. In question 5, in which liquid solvent would the solubility of lithium chloride be lowest? Because lithium chloride is an ionic compound, it should be soluble in something that is aqueous or something that is polar. So ammonia is polar, cyclohexane is not, methanol is polar, and water is polar. So the lowest solubility is going to be in something that is non-polar, and this is going to be cyclohexane. In question 6, which compound does not contain an element with an oxidation number of -1? In hydrogen fluoride, the fluorine is -1. In sodium hydride, this is -1. In hydrogen peroxide, that is -1. This does not have anything in oxidation state -1, so D is the answer. In question 7, which reaction involves the oxidation of a group 7 element? So there is no element in B as well as D. Those are ruled out. But in C, we have element fluorine. However, it's not oxidized. We can see fluorine becomes fluoride, so that is out. Here we have bromine in oxidation state 0 and fluorine in oxidation state 0. In this case, we form one product. In this compound, because fluorine is more electronegative, it's going to have oxidation state -1, and bromine will have oxidation state +1. So bromine is oxidized as fluorine is reduced, so the answer should be A. In question 8, equivolumes of some 0.01 mole per decimeter cubed solutions were mixed. Which pair of solutions gave the greatest mass of precipitate? Now, when we mix barium chloride and silver nitrate, we can produce barium nitrate and silver chloride. This is going to be aqueous. There is only one solid formed. In here, we will get barium sulfate and silver chloride, which are both solids. So all products are going to be in solid state. Here we'll produce barium nitrate and sodium chloride, which are all aqueous. And here we can produce barium sulfate and sodium chloride. It's only barium sulfate that is going to be a solid. So the correct answer is going to be B because all products are going to be in solid state. In question 9, which test reagent could be used to identify an aqueous solution containing hydrogen carbonate ions? Hydrogen carbonate ions can be tested by adding an acid so that CO2 is going to be produced. The only acid among the compounds given here is going to be nitric acid, and therefore C is the answer. In question 10, bromine liquid can be disposed of safely by reacting with aqueous sodium thiosulfate. So they've given us the equation for the reaction. And they say, what is the minimum volume in centimeters cubed of 0.5 mole per decimeter cubed sodium thiosulfate needed to react completely with 0.01 mole of bromine. So because this is a complete reaction, and we know the moles of bromine, that has to be completely finished. So the number of moles of sodium thiosulfate are going to be 2 times the moles of bromine, which gives us 0.02 mole. So the volume of sodium thiosulfate required is going to be number of moles divided by concentration, which is 0.02 divided by the concentration, which is 0.5, and the answer is equal to 0.04 decimeters cubed. However, this question wants us to give the answer in centimeters cubed, and so we have to multiply by 1000, which is going to be 40 centimeters cubed, and this is going to be the answer. In question 11, what is the mass of nitrogen atoms in 50 centimeters cubed over 2 mole per decimeter cubed solution of ammonium nitrate? So they've given us the volume as well as the concentration. The moles of ammonium nitrate will be the concentration, which is that times the volume, and multiplied by 10 power negative 3 to convert the volume to decimeters cubed. And the number of moles I got was 0.1 mole. So the mass of ammonium nitrate is going to be number of moles times molar mass, which is 0.1 times 80, giving me 8 grams. So since in this compound we have 2 atoms of nitrogen, the percentage of nitrogen by mass is going to be 2 times 14. Divide by 2 times 14 plus 4 plus 48. This is the total molar mass, which we can see here, times 100, giving me 35%. So 35% of the total mass is going to be the mass of nitrogen. So mass is equal to 35 divided by 100, which is 35%, times 8, giving me 2.8 grams. So the answer is going to be a C. In question 12, which row shows the correct trend down the group of the elements of group 7? Down group 7, the boiling temperature increases because there are more London forces due to the increase in the number of electrons or the increase in molecular mass. Electronegativity will decrease, and reactivity as an oxidizing agent is going to decrease, so the answer is going to be A. In question 13, which statement best explains why the rate of a chemical reaction increases with increasing temperature? If temperature increases, the reactants will have more energy equal to or greater than the activation energy, so the frequency of successful collisions will increase, and therefore the answer is going to be D. In question 14, which statement is not true for a system at dynamic equilibrium? The first part says the position of equilibrium is affected by the temperature, by pressure, and catalyst. That is not true. At equilibrium, the catalyst has no effect. The concentration of reactants is constant. This is true. The concentration will not change when dynamic equilibrium is reached. The next says the forward and backward reactions occur at equal rates. That is true. And the equilibrium can be reached from either side. That is also true. So the answer is A. In question 15, silver nitrate in aqueous ethanol is added separately to 4 halogenoalkanes, which would form a silver halide precipitate in the shortest time. Because they're all halides on carbon 1, the weakest bond is going to lead to the halide ion breaking away easily in order to attach to the silver to produce a halide precipitate. So because the carbon iodide bond is the weakest, the precipitate is going to be formed in 1-iodobutane. So the answer is D. In question 16, which is the total number of structural isomers for cyclic alcohols with a molecular formula carbon 4 hydrogen 8 oxygen. So because all these are cyclic isomers, we could have 4 carbons and then an OH on any of the carbons, or it could be 3 carbons, 1 CH3 out, and then OH. It could also be 3 carbons, another carbon, and OH. Actually, I could correct this. So this could be like that. 3 carbons inside, another carbon here, and then OH. It could also be 3 carbons, 1 CH3 out, and OH. So there are 4 possible cyclic isomers, and the answer is going to be C. In question 17, which is a correct equation for the incomplete combustion of butane 1O? If it's incomplete combustion, then it means not only carbon dioxide and water. So this is going to be out, and that is going to be out because these show complete combustion. That leaves us with these, but this equation is not balanced, so the answer is going to be a C. In question 18, which reagents could be used to produce a chloroalkane from a tertiary alcohol. So we can use PCl5, we can use concentrated HCl, and we can also use concentrated sulfuric acid plus potassium chloride. So the answer is going to be A, or reagents could be used. In question 19, what amount in mole of the oxidizing agent is needed to convert 1 mole of pentan 1,3,5-triol into 3-oxopentane-dioic acid and water? This is converting this compound here to that compound. And since this is going to be converted to an aldehyde and then a carboxylic acid, we'll need 2 moles of the oxidizing agent for this one. We'll also need 2 moles of the oxidizing agent for this one. But this one is going to be converted to a ketone, so just 1 mole of the oxidizing agent is going to be required. Therefore, in total, we'll need the 2 plus the 2 plus the 1, creating 5. So the answer should be D. Question 20. Which compound gives the mass spectrum? So here we have the molecular mass equal to 58. And we have an outstanding peak at 43 as well as a peak at 15. If you add up the molecular mass, it's either going to be this compound here or the aldehyde. However, there is no peak at 29 that would be present in this one. So the answer is going to be B. It's only the ketone. So this brings us to the end of section A. Let's continue to section B. In question 21, this question is about the element calcium and some of its compounds. Give the complete electronic configuration using SPD notation of a calcium atom in the ground state. This is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And in part B, calcium reacts with chlorine to form calcium chloride, as we can see in this reaction. They say explain in terms of oxidation numbers why this is a redox reaction. This is a redox reaction because calcium is converted from oxidation state 0 to oxidation state 2 plus, and chlorine from 0 to -1. So calcium is oxidized while chlorine is reduced. And since oxidation and reduction occur, that is a redox reaction. And down here they say complete the table to indicate the type of bonding and structure in the species involved in this reaction. Calcium is going to be metallic and the structure is giant. Chlorine is going to be covalent, the structure is simple. And then calcium chloride is ionic, the structure is going to be giant. Again, remember, all ionic compounds are going to be giant structures and all metallic compounds are giant structures. And next it says state the expected flame color when calcium chloride is used in a flame test. The color is going to be orange-red. In part C, a sample of solid anhydrous calcium nitrate is heated strongly for several minutes in the apparatus shown. So we can see in the end we have water containing the universal indicator and then calcium nitrate. This is thermal decomposition and we're going to produce nitrogen dioxide, oxygen as well as an oxide of calcium. So they state 2 observations that would be made. Here a brown gas is going to be produced, that gas is nitrogen dioxide, and then bubbles will be produced in the water, and the universal indicator color is going to turn red, nitrogen dioxide. It is an acidic gas, so the indicator solution is going to turn red. Next they say explain why the observation from C1 would be made more quickly if the experiment was repeated with solid anhydrous magnesium nitrate. The decomposition of magnesium nitrate is faster in comparison to the decomposition of calcium nitrate. So I said magnesium nitrate has less thermostability in comparison to calcium nitrate because the magnesium 2 plus cation is smaller than the calcium 2 plus cation. So the Mg2 plus has greater charge density and greater polarizing power on the electron cloud on the oxygen in the magnesium-oxygen bond. So the nitrogen-oxygen bond in the magnesium nitrate is weakened more, requiring less energy to be thermally decomposed. So my demonstration is here. We can see the electron cloud on oxygen is going to be distorted and this bond is going to be weakened, so less energy will be required to decompose here in comparison to that. And in part D, they say samples of calcium and magnesium are added to separate test tubes of cold water containing a few drops of universal indicator. State and explain the differences in the observations made in each experiment. include an equation in your answer. So because this is cold water, the reaction with calcium is going to be a little bit faster in comparison to the reaction with magnesium. When magnesium and calcium react with water, they will produce hydroxides, but the magnesium hydroxide is more insoluble in the water in comparison to calcium hydroxide. So there will be a precipitate visible in calcium hydroxide, and it's going to appear faster in comparison to the tiny or slight precipitate visible in magnesium hydroxide. So I said calcium is more reactive with cold water than magnesium, so more effervescence or bubbling will be observed with calcium than with magnesium. The reaction of a metal with cold water yields a metal hydroxide and hydrogen gas. According to this equation, we can see a reaction between calcium and water. Effervescence will be observed, and that is because that gas is going to be produced. So on addition of a few drops of universal indicator, the color of the indicator will turn blue. In the reaction with magnesium, a white precipitate is formed faster, while in magnesium, the precipitate may not be observed. These observations are because calcium has more shells than magnesium, so the outer electrons in calcium experience greater shielding, making the reaction to form calcium 2+ easier. Also, calcium hydroxide formed is more soluble in water than magnesium hydroxide, and the magnesium hydroxide formed coats on the surface of magnesium, preventing further reaction. So this brings us to the end of question 21. Let's continue to question 22. In question 22, this question is about enthalpy changes. A student wanted to use Hess law to determine the enthalpy change in kilojoules per mole of reaction 1. So this is reaction 1. Explain why the enthalpy change of reaction can be described as enthalpy change of formation. In this reaction, the reactants are all elements at standard conditions, so the enthalpy change of this reaction is the enthalpy change of formation, and actually 1 mole of product is produced. So I said because the reactants, magnesium and oxygen, are elements in standard state, also 1 mole of magnesium oxide is produced. In part B, the student carried out an experiment to determine the enthalpy change of reaction in kilojoules per mole for reaction 2, which is this one here. 0.189 grams of solid magnesium oxide was added to excess hydrochloric acid in a polystyrene cup and stirred until the reaction was complete. The total mass of the solution formed was 25 grams. During the experiment, the temperature increased from 21.5 to 28. Calculate the enthalpy change of reaction 2 in kilojoules per mole, including a sign. They say give your answer to an appropriate number of significant figures, and they've given us the specific capacity of the solution. So to do this, I can say Q is mc delta T. Since the solution is 25 grams, so the mass is 25 times the given specific capacity times the temperature change, which is 28 minus 21.5, and I got 679.25 joules. Dividing by 1000, I got that in kilojoules. Also, because they use 0.18 grams of magnesium oxide, I can use that to calculate the number of moles, but I need to find the molar mass, which is 40.3 grams per mole. So the number of moles of solid magnesium oxide used is going to be the mass divided by the molar mass, giving us that in moles. And therefore, delta H is going to be negative Q over N, because this is an exothermic reaction. Dividing that by that gave me negative 145 kilojoules per mole to 3 significant figures. In part C, calculate the enthalpy change for reaction 1. Use your answer in B, the data provided, and the enthalpy cycle shown. If you did not calculate the answer in B, use the value negative 100 kilojoules. This is not the correct answer. So this is the data given to us. Here we can see magnesium reacting to give us that. It's going to be negative 462 kilojoules per mole. That is this first reaction. And the other reaction is going to be hydrogen plus oxygen to give us water, which is going to be this one here, because we can see magnesium chloride is still magnesium chloride here, but the other 2 components react to form water. From the previous reaction, we calculated negative 145 kilojoules per mole. So if we're trying to find this, it's going to be negative 462 minus 286 plus 145. And this gave me negative 603 kilojoules per mole as my answer. So this brings us to the end of question 22. Let's continue to question 23. In question 23, this question is about bromoalkanes with the molecular formula carbon-4 hydrogen 9Br. Give the IUPAC name of the only carbon-4 hydrogen 9Br tertiary bromoalkane. The compound they're talking about is this one here. So the name is going to be 2-bromo 2-methylpropane, and this is going to be the answer. Draw the displayed formula of the only carbon-4 hydrogen 9Br secondary bromoalkane. It means the Br is going to be on carbon 2 and all the other carbons are going to be laid out in a chain. So this is going to be the structure. And next they say draw the skeletal formula of the only branch chain carbon-4 hydrogen 9Br primary bromoalkane. Because this is the only branch chain, it's going to be similar to that. And since they've told us skeletal formula, we have one carbon, the second, the third, and then the fourth, and then a bond connecting to Br. And in part B, give the structure of the carbon-4 hydrogen 9Br bromoalkane that would react fastest with aqueous silver nitrate in ethanol. Again, this is going to be the tertiary one. So this is going to be this structure here. In part C, some reactions of CH3CH2CH2CH2Br are shown. So we can see reaction 1, converting Br to OH, that is going to be reaction with potassium hydroxide in aqueous. Reaction 2 is converting to an alkene, so this is going to be reacting with potassium hydroxide in alcoholic conditions. And then here we can see this is going to be a reaction with potassium cyanide, and here a reaction with ammonia in a sealed tube. So they say complete the table. Like I've already said, reaction 1 is going to be a nucleophilic substitution reaction with potassium hydroxide, or it could be sodium hydroxide, but the conditions are going to be aqueous and there is need to heat. The second reaction is elimination. A Br and a hydrogen are going to be lost. So here we'll need potassium hydroxide, but it has to be heated in presence of an alcohol. Reaction 3, we're producing an amine. It's a nucleophilic substitution reaction with ammonia in alcoholic conditions, and we heat in a sealed tube because ammonia is a gas. Reaction 4 is a nucleophilic substitution reaction and KCN is used. We heat in ethanol. Next they say, complete the mechanism for reaction 3, include curly arrows and any relevant lone pairs, dipoles and charges. Here we have the NH3 with a lone pair on nitrogen, and then we have the carbon Br bond, which is polar, so I position sigma plus and sigma minus. The lone pair is going to be donated to the electron deficient carbon, and that bond is going to break away. So the Br becomes bromide. And in the next step, another ammonia comes and donates electrons to the hydrogen, and this bond breaks, returning the lone pair, so the hydrogen goes away. And in the end, we're going to have this and ammonium. Give the wave number range of an absorption in the infrared spectrum of an organic product of reaction R4, which is not present in the infrared spectrum of this one here. Going back to the reaction, we can see the product from R4 is going to be a nitrile. It means the carbon-nitrogen triple bond is going to be absent, so the wave number range should be 2260 to 215 per centimeter, and this is going to be due to the carbon-nitrogen, because all the other bonds are present except the carbon-nitrogen triple bond. So this brings us to the end of question 23. Let's continue to question 24. In question 24, the elements of group 7, the halogens, have many important uses. Fluorine is used to make sulfur hexafluoride, a gas which is used as an insulator in electrical equipment. Chlorine is used as a bleach and as a disinfectant in water treatment. Bromine is used to make organic chemicals that are used as fire retardants. Iodine has been used in the catalyst in the manufacture of ethanoic acid. In part A, sulfur hexafluoride can be made from the reaction of sulfur 8 with fluorine. So this is the reaction, and they say the structure is as shown here. They've given us the bond enthalpy data, and they say calculate the mean bond enthalpy in kilojoules per mole for a single bond. So if we go back here to the reaction, the enthalpy change is going to be the summation of bonds broken minus the summation of bonds formed. So here we have 8 sulfur-sulfur bonds, So the enthalpy for that is going to be 8 times 268. In here we have 24 fluorine-fluorine bonds. So it's going to be 24 times 151. And then for the product, we have 6 and then 8. So it's going to be 48 sulfur fluoride bonds. And this is why we have this here. The enthalpy change is given to us. So the given enthalpy change, which is negative 9672, is equal to that. And in the end, the sulfur fluoride bond is going to be 321.67, which is approximately 322 kilojoules per mole. I rounded off to 3 significant figures because these values were also given in 3 significant figures. Next, they say give 2 reasons why your answer in A1 is unlikely to accurately represent the true SF bond enthalpy in SF6. This is because in my calculation, I've used mean bond enthalpies, which are number one averaged over a number of compounds, and it's because they're used in gaseous state. So I say the mean bond enthalpies used are for data in gaseous phase. Also, the values are averages for various compounds. Next, they say SF6 is a potent greenhouse gas. 1 gram of SF6 absorbs the same amount of infrared radiation as 23.9 kilograms of carbon dioxide. Calculate the number of molecules of carbon dioxide to the nearest whole number that absorb the same amount of infrared radiation as 1 molecule of SF6 in the atmosphere. So I began by calculating the molecular mass of SF6, which is going to be the composition of sulfur plus 6 times the composition of fluorine, giving me that. So the moles of SF6 in 1 gram are equal to mass divided by molar mass. Remember, this is 1 gram, giving me 1 divided by 146.1, and those are the moles I got. Also, the moles of carbon dioxide in 23.9 kilograms are going to be 23.9 times 10 to the power 3, converting the kilograms to gram, divided by the molecular mass of carbon dioxide, and that gave me those moles. So in the end, I had to find the ratio of the carbon dioxide moles to SF6 moles, which was that to that, giving me 1 to 79359, and therefore there were 79359 molecules of carbon dioxide. In part B, bleach, which is that is formed by the reaction of chlorine with cold dilute aqueous sodium hydroxide. This is the equation for the reaction. The following species and equilibria are present in solution of sodium chloride 1, which is that. So equilibrium 1, we can see that converted to that, we see equilibrium 2 as well as equilibrium 3. And they say household bleach is stored at a pH between 11 to 13. Household bleach should not be stored near strong alkali. Give the formula of the chlorine-containing species present at highest concentration in household bleach at pH 12. When the pH is 12, this is going to be neutralized. So the forward reaction is going to occur in this case, producing more of this. So it's going to be ClO minus. Explain why mixing strong acid with bleach is dangerous. Justify your answer using the equilibrium shown. If you add strong acid, it means you're going to increase the H+ ions. And in this case, the reaction is going to go to the forward reaction, producing chlorine, and we know chlorine is toxic. So for reaction 1, it's going to form the other side, producing the acid and decreasing the effectiveness of the bleaching agent. So I said a higher concentration of H+ will shift the equilibrium 2 forward. Chlorine will be produced and chlorine is toxic. Also, equilibrium 1 shifts backwards, producing HClO, decreasing the dissociation of ClO minus, weakening the bleaching effect. On heating, sodium chloride 1 decomposes to form sodium chloride and sodium chloride 5. Give the equation for this disproportionation reaction. Set symbols are not required. So sodium chloride 1 gives us sodium chloride and sodium chloride 5. This is going to be a 3, that is a 2, and that is a 1. And in part C, they say the structure of a fire retardant is shown. Calculate the percentage by mass of bromine in the fire retardant. Give your answer to an appropriate number of significant figures. I'm going to take time to cut this out so that you guys can see how the structure looked like initially. And then I will return the bonds that I had included. So I included the carbons and the tiny bonds to show how many carbons and hydrogens are present. And if you count, you'll see that there are 12 carbons, 18 hydrogens, and 6 bromines. So the molecular mass is going to be the number of carbons times 12 plus the number of hydrogens times 1 plus the number of bromines times 79.9, giving us 641.4 gram per mole. And the percentage by mass is going to be 6 times 79.9, which are the bromines, divided by the total times 100, giving us 74.7%. The industrial manufacture of ethanoic acid first used an iodine-based catalyst. Explain with the aid of the labeled Maxwell-Boltzmann distribution how a catalyst increases the rate of a chemical reaction. So on the vertical axis we have number of particles, and on the horizontal axis we have energy. We will have EA, or activation energy, for an uncatalyzed reaction, as well as the activation energy for a catalyzed reaction. The one for the catalyzed reaction is going to be lower than that for the uncatalyzed reaction. And from this diagram we can see the number of particles with energy equal to or greater than the activation energy in an uncatalyzed reaction is going to be less than the number of particles with energy equal to or greater than the activation energy when the reaction is catalyzed. So I said using a catalyst creates an alternative pathway with lower activation energy, so more particles have energy equal to or greater than the activation energy, so more successful collisions occur per time, increasing the rate. So this brings us to the end of question 24, as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.